Today we're talking about the VSEPR model, which is the valence shell electron pair repulsion model. This helps us to predict the 3D structure of a molecule based on the fact that electrons repel each other, and so the electron pairs in a molecule want to be placed as far apart as possible. So again, we're looking at 3D structures. Our Lewis structures are a good representation of the molecule on paper, but they don't give us the full picture because molecules aren't necessarily flat. So this model is used to predict the 3D structure of covalent compounds, mostly for simple structures. The main rule is that the electron pairs repel each other, and so they want to be as far apart as possible. And in our structures, those electron pairs are going to be our lone pairs and bonds. So lone pairs and bonds want to be as far apart as possible. So the steps for drawing or figuring out the VSEPR structure for a molecule is to first start by drawing the Lewis structure. You have to do this before you figure out the VSEPR model, so don't skip this step. Next is to count up the electron regions around the middle atom. So electron regions can be lone pairs or bonds. We want to have them arranged as far apart as possible to minimize the amount of electron-electron repulsions. So when you're counting up the electron regions, a double or a triple bond only counts as one electron region. A single bond counts as one electron region, and one lone pair counts as one electron region. We can figure out where those atoms are going to be from the way that the electron pairs are shared and distributed so that they're as far apart as possible. So we can look at the number of electron regions and whether they are lone pairs or bonds to determine the name of the molecular shape. And then we can see the structure, the 3D structure of that molecule. So lone pairs influence the bond angle. The bond angle is how far apart those bonded atoms are. And so the more lone pairs we have on an atom, the smaller our bond angle becomes. Lone pairs require a lot more space than a bond, and so it compresses the angle between the bonding pairs. So for example, in CH4, there is no lone pairs on the central atom, and so we're going to have a larger bond angle. In NH3, there's one lone pair, so that bond angle starts to become compressed. So we went from 109.5 degrees to 107. In water, there's two lone pairs on the central atom, so our bond angle becomes even smaller, decreasing to 104.5. So just a few rules for VSEPR. First of all, if there's only one or two electron regions in the molecule, it must be a linear molecule. If the molecule has 3 electron regions, it will be trigonal planar. If it has 4 electron regions, we start to have options. So we have tetrahedral, trigonal pyramidal, and V-shaped or bent. And these depend on the number of bonds and the number of lone pairs that each has. If there's 5 electron regions, we start to get even more options: trigonal, bipyramidal, seesaw, T-shaped, linear. And again, those are dependent on how many bonds and how many lone pairs we have. If we have 6 electron regions, we can have octahedral, seesaw, or square planar. Again, looking at how many lone pairs and bonds there are. In example 1, we want to find the molecular shape for H2O, water, and NH3, which is ammonia. So let's start with H2O. The first step is to draw the Lewis structure for the molecule. So again, for Lewis structures, we count up our valence electrons. figure out our central atom. And then in this case, we have hydrogen, which is an exception. It does not want more valence electrons, so we're going to add our remaining electrons to the central atom. All right, so to figure out the molecular shape, we look at this central atom and we count up how many electron regions there are. So we have 2 bonds and 2 lone pairs, so total we have 4 electron regions. So the shape of our electron regions, because we have 4 of them, is tetrahedral. And then the shape of our bonds, we only have 2 of those. We have 2 lone pairs. So the shape of the bonds is bent. For ammonia, we do the same thing. We count up our valence electrons. Figure out our central atom. Connect with single bonds. And again, we have hydrogen as our outer atoms. So those don't need any additional electrons, so our leftover 2 go on the nitrogen as a lone pair. So here we look at, again, the number of electron regions. And we have 3 bonds and 1 lone pair, so 3 plus 1 is 4. So the shape of the electron regions, again, is tetrahedral because there are 4 of them. But the shape of the bonds, since there's only 3 of them and 1 lone pair, this time the shape of our bonds will be pyramidal. Example 2 says, because the noble gases have filled s and p valence orbitals, they were not expected to be chemically reactive. In fact, for many years, these elements were called inert gases because of the supposed inability to form any compounds. However, in the early 60s, several compounds of krypton, xenon, and radon were synthesized. For example, a team at the Argonne National Lab produced a stable colorless compound called xenon tetrafluoride. Predict its structure and whether it has a dipole moment. So xenon tetrafluoride is going to be XeF4 based on our naming. Tetra is 4. So the first thing we need to do is draw its Lewis structure. So for xenon we have 8 valence electrons. For fluorine we have 7, and there's 4 of them. So we have 36 electrons total. I put my xenon in the middle because it's the only one of its type, connecting them with single bonds. And then I fill in the octets of my outer electrons, or atoms. I wind up with 4 electrons left, and the rules say for Lewis structures, whatever we have left over goes on the central atom in pairs. So I'm just going to put pairs on my xenon, which is fine because xenon is one of the exceptions that allows us to have more than 8 valence electrons. So to figure out the shape of this, I first look at my number of electron regions. So for xenon, I have 1, 2, 3, 4, 5, 6. I have 4 bonds and 2 lone pairs. So we have 6 electron regions. When we have 6 electron regions, that means it's going to be octahedral in shape. However, I only have 4 bonds. 2 of those regions are lone pairs. So the shape of my bonds is actually going to be square planar. So the second part of this question asks us to find out whether this has a dipole moment. So in order to figure that out, I actually need to draw the 3D structure of this molecule. So to draw a square planar, I'm going to have two of my fluorines coming towards us and two going away from us. And then to show these lone pairs on the xenon, I'm going to have one coming above the xenon and one below it. So to look at my polarities, we know that fluorine is the most electronegative element on the periodic table. And so all of my dipole moments are going to be pointing outwards towards those fluorines. So my fluorines have this slightly negative charge, and that's going to give my xenon a slightly positive charge. Well, now to figure out if the molecule is polar, I need to see if I can divide this in any way that keeps that positive charge and those negative charges separate. And I don't see any possible way to do that. That positive charge is kind of trapped in the middle there. And so this is non-polar, or we can say it has no dipole moment. So some molecules have double or triple bonds. An example is NO3- has double bonds in it. However, when we're dealing with VSEPR, we don't really consider those double or triple bonds to be any different than a single bond. We treat them as one electron region. If there's resonance structures of a molecule, NO3 also has resonance structures, we can use any of those resonance structures to predict the molecular shape, especially if they're all equivalent resonance structures. We can use any one of them to predict the molecular shape because the resonance structure is just moving those double bonds around the structure, and it's not going to affect how many electron regions our atoms have. In this example, we're asked to find the molecular structure for sulfur dioxide and then decide whether or not it will be polar. So sulfur dioxide is SO2. For sulfur, we have 6 valence electrons and 1 sulfur. For oxygen, we also have 6, but there's 2. So total, we have 18 valence electrons. To draw my Lewis structure, I put the sulfur in the center. Draw the oxygens with single bonds. And then I can start filling in my valence electrons on the outer atoms. The remaining 2 will go on the sulfur in the middle. So what we see is that sulfur does not have a full octet. And so I need to fix that by creating a double bond. So now everything has a full octet. However, we can actually make this more stable by taking this and making a double bond as well, because now if we look at formal charge, we would have 6, 5, 4, 3, 2, 1, 0, 6, 5, 4, 3, 2, 1, 0, 5, 4, 3, 2, 1, 0. And that gives us all zeros. So this is what our most stable structure would look like here. So when we count up electron regions around our central atom, remember the double bonds only count as 1 each. We don't count them as multiples because it's just one place with electrons. So our sulfur has 2 bonding regions and 1 non-bonding. So it has 3 electron regions. So the shape for 3 electron regions is trigonal planar. But because we have 2 bonds and 1 lone pair, the bonding shape is going to be bent. All right, so to figure out whether or not this is polar, we'll draw the bent molecule. So sulfur is less electronegative than oxygen. So my poles are going to be pointing towards these oxygens. So the oxygen side will have a negative charge, slightly negative charge, and the sulfur will have a slightly positive charge. And what we can see here is that we can actually split this horizontally down the middle, and we wind up with our negative pole on one side and our positive pole on the other. And so this is a polar molecule. It does have a dipole moment. So some molecules have no central atom, or they have, it seems like, multiple central atoms. So in order to figure out the shape of it, we need to look at the different central atoms that could be considered central in the molecule. So for example, CH3OH is one that has two atoms that could be considered central. So we have the carbon here and the oxygen here in red. So the carbon has 1, 2, 3, 4 electron regions. And so all of those are bonds. So it's going to be a tetrahedral shape. The electron regions and the molecule structure will be tetrahedral because it has 4 electron regions, all of which are bonds. The oxygen has 1, 2 bonds, and then it also would have 2 lone pairs. So it also has 4 electron regions, which is tetrahedral. However, the structure of the bonds is going to be V-shaped or bent because it only has 2 bonds and 2 lone pairs. So when you run into a molecule with no central atom and you're asked to find the shape, just look at each quote unquote central atom individually and figure out what shape that would be to look at the shape of the overall molecule.